Hello everyone, welcome to this LeetCode daily where we are going to go through find in the mountain array, which is a problem where you receive as input an array of integer and a target. And you're supposed to find the first occurrence of the target in the mountain array. So in this problem we have a couple of constraints. The first is that you don't have all the elements at the beginning. But you do have some method that you can use to get a specific element in the array. And the second thing is that you have a limit on the number of requests you can perform on the array. So that being said, how are we going to organize ourselves to solve it? Before solving it, we need to understand what is it, have some example, and try to come up with an approach that will help us to solve the problem. So before diving into it, if you're new here is Argo Architect. Here we are solving LeetCode daily occurring solution. So if you're interested in any of those topics, don't hesitate to subscribe to not miss what we are doing here. So let's start. So like we said, we have an array which is a mountain array. A mountain array is basically an array which is separate into two parts. I would say we have an ascending part and a descending part. So a mountain array will always behave like this, right? It will climb and it will go down like this. This is an example of mountain array. This is an example of mountain array. So and then you have a given target that you're supposed to search, and you're supposed to search the target into your mountain array and return the first occurrence of that target. What does that mean? That means if the target is maybe this element, if this value is the same here, you should return this one. If the target is here, you should return this one, right? So to validate if what we are thinking about is exactly what we are supposed to do, that means searching in an array an element, it look easy, right? Let us do something easy to just validate that. So what we are going to do is that we are going to initialize our index to 0, that means the first element, and then we are going to say while we are not at the end of the array, let us take the element, compare it to the target, and if it's equal to the target, we return. So this is what we are trying to do. So we are looping from left to right, and if we find a target, we return the target. Basically, if you have two targets, the first one will be found first. So let us submit this and see. So if we do so, we are going to see that okay, it is working. That means we are correct about the fact that what we need to do is just about searching an element in an array. But just that we have constraint here, the first constraint I just mentioned, you can't make more than 100 call. And then if you have an array of 100 elements, basically even this approach will help you to achieve the result with less than 100 call, because the array has just 100 elements. But here is not the case. Here your array can go up to 10 power 4, so this will not help you to pass all the solution. Now you know what you're supposed to do, you know what is blocking you from passing all the solution, and now you should think of an approach that will help you to cross this boundary of 10 power 4. And then since we have an array which is actually increasing and an array which is actually decreasing, we should think of binary search. And before thinking of binary search, we need to evaluate, is binary search actually enough to solve this problem? So we know that binary search is actually solving the problem is big of log of n. So the question is, what is the number of calls we can have with log of n given this input? So you can compute it easily by just say you can just compute it log of 10 power 4 divided by equal to this divided by log of 2. This is the number of calls that you expect to have with an input 10 power 4. So average 14 call. Okay, nice. We have an average of 14 call. So if you use a binary search, we are going to have the result into average 14 call, which is actually less than 100, which is nice, which is something we want. But we know that binary search can be applied on an array which is in a sorted array, right? But our mountain array is not sort. How can we organize ourselves to make it sort? So basically we have an array which is climbing and going down. So we have two parts of the array which are actually sort. So what we can do is that we can divide our array into two, and then take the first part which is sort, apply the binary search in it, search for the element, and go to the second part, apply again the binary search and search for the element, and if the element is not found in the first and the second one, then we return -1. So basically that will be our goal here. To separate the array into two arrays, we need to find the peak element. So the first thing we are going to do is find the peak element. The second thing is search into the first array. The last thing is to search in the second array, and we are going to return the result at the end. And then you may ask yourself, by doing all those two operations, are we still going to perform less than 100 requests? And the answer is yes, because we are going to search the peak using binary search, which is average 14. We are going to search to the left using binary search, which is average 14, and we are going to search to the right using binary search, which is also average 14, which gives you 40 something, 42. Now we are going to say that it's a little bit above the 42 requests, but it's still less than 100 requests. So we are 100% sure that with that approach we can indeed find ourselves in the boundary and have the result. Now the next thing is how to find the peak. So for us to search the peak, we are going to use a binary search, and then what we are going to have is something like this. We are going to have a starting point here, which is the first element of our array, and we are going to have an ending point here, which is the last element of our array. And basically what we are going to do is that we are going to find the middle of this element, and in the first case it will be here. And what we are going to say is that if that middle is actually less than the element just after him, that means the peak is in the subarray greater than the middleware, the temporary peak. Otherwise, that means the peak is actually in the left array. So if in the first case the temporary peak, that means the middle, is actually less than the element plus 1, that means this one can be shifted to the peak plus 1, right? And otherwise, that means the first element can be shifted to the peak, right? So that's what we are going to implement here. Our approach now will be, we are going to find the peak. We are going to say, okay, while we haven't met, while the end is not equal to the start, we take the peak as the middle element, that means the start plus the difference divided by 2, and then we are going to check if the peak, the mountain peak, is actually less than the mountain peak plus 1, then we are going to say the start will move to peak plus 1. It's exactly what I just explained here. Now you understand why I was saying that you have more than 42 requests, because here you are calling for the peak and you are calling for the peak plus 1. So basically you can say that your searching peak is actually 2 times log of n, and the search in ascending will be log of n, and in descending will be log of n. This is actually 4 times log of n, which is still something acceptable, right? So this is something we can go with without being afraid of falling into out of boundary. So let us continue with our peak function. We are able to have the peak with this approach, and then at the end the peak will take the start. So at the end, basically the peak is the start, the end will be equal to the start, so the peak can take the start or the end. Now that you have the peak, you need to perform the search. So this is literally the binary search that we did yesterday and the day before yesterday. We applied binary search, and yesterday we used built-in binary search. The day before yesterday we used a modified binary search. So this is definitely the week of binary search. Check out the previous video if you want to know more about binary search. But in binary search, you definitely search an element into a sorted array, given that you know the element, right? So what we are doing here is the binary search. We define a middle element, we get that element, we compare the element to the target that we are searching. If it's equal, then beam, we have it, we return. If it's not equal, then we move, then we perform a check. If it's not equal, we are going to check is actually the element. Let me take this so you understand better. Let's say we are searching an element here, and then let's say we have this element is actually 1, this element is 6, this element is 18, this element is 20, and this element is maybe, maybe put 40, this element is actually 50, right? So what you are doing is that, let's say we are searching for 6, we are searching for 6, for instance. If you are searching an element in a binary search, in a binary way, you are going to define the starting point, the first element, and the ending point here. So you have the ending point here, and then you are going to define the middle. In this case, the first middle will be this, and the idea is that you are going to compare this middle to the element that you are searching. Let's say we are searching for 6, for instance. You're going to say, okay, is 6 actually greater or equal? Is 6 actually equal to the middle element? No, it's not actually equal to the middle element, so we don't return it. We are going to check, okay, is actually 6 less than the middle element? Yes, it is less. If it's less, so you just move this end pointer to the position target -1. If it's not the case, if you were searching maybe for 14, you will see that it's actually the middle element less than the search element. Yes, if it's less, now you are going to instead move this one forward. So basically the idea is always to kind of split the array into 2 subarray by saying that, okay, the array is sort. If I'm searching for this element, which is not at the position that I was thinking it was, what part of the array is my element? Is it the upper bound or the lower bound? Because each of the iteration will actually split your input into 2. So it will either be in the array consisting from the middle to the end, or from the middle to the 0. So each iteration is going to split. That is what make it to be log of n. So by doing so, you are able to have the result in case it exists. If it doesn't exist, you are going to twist, you are going to move left right until you find that your both indexes, the start and the end, are actually equal. In that case, that means the array doesn't exist. If it doesn't exist, you are going to search now in the second part. Now searching in the second part is basically the same, but just that the check is actually different, right? Since you are actually in a descending array, you're just going to say if the current element is actually greater than the target, instead of updating the end, you're actually updating the start, because the array is actually descending. And at the end, if you don't have the answer here, that means it is not in the first array, it's not in the second array, so it doesn't exist. We return -1. So this was my approach of solving this. I hope you do enjoy it. Let us run and see what it gave. You see, it's actually performed well. So this is what we have. You see, we have 0 millisecond. It's actually performing pretty great. We have all test cases green. So this was my approach of solving this. I hope you do enjoy it. Feel free to leave me any comment. I'll be really happy to interact with you regarding this. See you on the next video. Ciao.